Now the topic of discussion is magnetic boundary conditions. Similar discussion we have done in case of electrostatics, where we derive the relation at the boundary between two medium, the nature of the electric field intensity and electric field density at the boundary. Here similar derivation we will do in case of magnetic boundary conditions. So for that purpose we will consider two medium having permeability 1 and permeability 2. The magnetic field in medium 1 is B1. Magnetic field means magnetic flux density, and the magnetic flux density in medium 2 is B2. So our concern is that when magnetic flux density is changing from one medium to another medium, what will be its characteristics. So for that purpose, this magnetic field has two components, that is tangential to the boundary, that is termed as B1T, and normal to the surface, that is B1N. Similarly, in another medium, when this magnetic field enters, there will be two components, B2T, that is the tangential component, and the normal component of this will be B2N. In this way, we can find the components of magnetic field density in medium 1 and in medium 2. So here what we can find, the tangential component is parallel to the surface, that is tangent to the surface. However, the normal component is perpendicular to the surface. And if we wish to find the characteristics of tangential and normal component at the boundary, for that purpose, let us consider the differential surface at the boundary. This is area is del S, and this is of thickness. Consider is the thickness of height of the cylinder is del H. We considered a differential cylinder at the boundary, and apply the Gauss law. We can say the B dot ds should be equal to 0 for any closed surface. Okay, and area vector of top surface is upward, and for bottom surface will be downward. Keep this in mind. Now for this closed surface, apply the B dot ds. So it can be, there are three surfaces. First is top surface, next is bottom surface, the third is curved surface. So one by one we will try to find B dot ds. From here one relationship can be find out. So for top surface we can say B dot ds. Similarly for bottom surface we can say B dot ds, and in continuation we can say B dot ds for curved surface. Okay, it must be equal to 0 because there are three surfaces only, and the sum of all should be equal to 0. And for the top surface at the boundary, there are two components of B. One is parallel to that, second is normal to that. So and area vector is normal to this. This is area vector, ds will be in the direction of this, and if two component of B, one in this direction, one in this direction, so dot product of this and this will give us some value, and the dot product of this and this will give us 0. So the tangential component will not contribute in this, only normal component will be there. Following that, we can say B1n ds is just differential volume and the angle between these two is 0. So cos 0 is 1. So for top surface, B dot ds will be B1n del s. And for bottom, similarly, the area vector will be the downward. So if it is considered in this direction positive, it will be negative in this direction. And B will be in this direction. B will be in this direction as it is given here. So for bottom surface, we can say B2n dot ds. ds is in opposite direction, so we can say, or we can say ds times the angle between these two, that is 180 degree. Cos 180 degree will give you -1. So from there we can say this, and this component, the tangential component, will make the angle 90, so it will give us 0. For curved surface, the area vector will be normal to the surface, that will be parallel to the, at every place it will be parallel to the, similar to tangent. So for curved surface it will be 0. Okay, so the net B1n del s minus B2n del s will give us 0. From here we can say B1n is equal to B2n. One thing we can say from this statement, that it is this similar relation we have derived in case of electrostatics, that is normal component of electric flux density is same. Similarly here, the normal component of magnetic flux density is same. So from here we can say normal component of B are same. Okay, so when the magnetic field changes from one medium to another medium, then the normal component will not change, it remains as it is. So we can say it is continuous. Normal component of B is continuous at the boundary. Continuous at the boundary of two medium. Okay. Now in continuation we can say the B can be written as mu1 h1n or n1. Okay, right, 1n is written everywhere, so write it h1n. And B2n can be written as mu2 h2n. So from here what we can say, h1n is not equal to h2n. We can say here. So it means the normal component of magnetic field intensity is discontinuous. So we can write here normal component of H is discontinuous. Okay, if it is continuous, then in changing the medium, the value remains same. However, it is different. So following that, we can say it is discontinuous at the boundary. From this equation we have b1n minus b2n is equal to 0. As this is normal component, so to write the normal component, we can say the dot product in the unit vector in the direction of normal b1 minus b2, it will give same value as it is. So this is the vector form of b at the boundary. Okay. Now similarly, let us try to find the relationship between the tangential component of h. For that purpose, consider the same here again, and for that purpose we will consider there is h1 and there is h2. At the place of magnetic flux density, we are considering now magnetic field intensity h1 and h2. The same way h1t and h1n, h2t and h2n. Same way as we have done here. The medium is same, mu1 and mu2, permeability of mu1, mu2. For this purpose, apply the Mps law. Take a loop. Here we are applying the Gauss law. Here we are applying Mps law. Take a loop, and in that loop h dot dl will be 0 because we have relationship. So in this one, the field will be inside. So name it from A, B, C, D. So just we have taken Amperian path that is enclosing. Now apply the Ampere's law, that is h dot dl for a loop will be equal to the current enclosed. We have studied this, and following this we can say that in this direction, start from here, I enclosed can be written as start from here, h for AB, for BC, for CD plus DA, including all it will give us current enclosed. Consider this thickness as delta H and this thickness as delta width. So considering this, for AB we can say H is, for this portion H is in this direction and the DH is in this direction, so it will be minus H1n del H by 2. For this portion I am writing H is in this direction and del H is in this direction, so both are in 180 degree opposed. So for that purpose, due to that, minus sign will be there, and H1n del H by 2. For BC, and for this portion we can write same as H2 is in this direction, del H by 2 is in this direction, so we can say H2n del H by 2. So from A to B we can write this. From B to C, this is H2T, however this is minus, this is del W positive direction. So del W and B both are in opposite direction, so here it should be minus sign. Minus sign will be H2T times del W. this is multiplication, not dot product, because minus sign is already placed here. So from C to D, H2n is in this direction, del H by 2 is in this direction, so both should be positive. H2n del H by 2 plus similarly here H1n del H by 2, H1t plus del W, both are in same direction, so it should be H1t del W. Combining all, it should be equal to the current enclosed. So from here we can say this term and this term will be cancelled out. This is, and if simplify, then we can have minus H2t del W plus H1t del W, and that I can be written as, I enclosed can be written as J dot ds. ds can be written as del W for unit length, we can say it is del W only. So here we can write J is del W. So from here we can write H1t minus H2t is equal to del S, J's current density. This is the ampere per meter. So what we find, the tangential component of magnetic field intensity is discontinuous. Now let us solve one example related to boundary condition in magnetic field. There is what's xy plane, means z is equal to 0. This is the plane. There are two different mediums, permeability 4, permeability 6. It is considered as magnetic field density in this B2. Here it is B1. At interface, current is given 1 by mu naught in the direction of AY, and this B2 is given as 5AX plus 8AZ. So normal component is 8AZ, tangential component is, this is x direction, so that is 5 in the direction of AX. If this is given, then we have to find H1 here, magnetic field intensity, and magnetic flux density in material 1. So for that purpose we have, this is the full problem, then we have B, this is the normal component, and this is in Z direction. The relationships that we derived at the boundary between B and H was B1n was equal to B2n, and from here mu1 times H1n, mu2 times H2n, we can write from here to here. And the third relationship was, that was H T1 minus H T2 was equal to the current density. So there were three relationships that we have derived, and from here, on the basis of this, we can find the H1 and B1. So let us start from the known value, that is B2. We know B2. So B2 has, this is B2. There are two components of it, B2n, B2t and B2n. N is in the direction of Z, as it is Z. So it is 8 and it is 5. Okay, so from here we can write B1n is equal to B2n as it is continuous. So that is 8 in the direction of AZ. So from here we can say B in the Z direction is 8. From here we can say B2 is equal to mu naught mu r H2. We can write this. So from here we can say H2 is equal to B2 plus 8AZ. B2 divided by mu r is 4 mu naught. So this is mu 2. Similarly H2. Similarly H1 can be written as B1 divided by mu naught mu r 1. So B1, we don't know B1, we have to derive. So for that we will assume that it is B1x in the direction of AX plus B1y plus B1z, we can assume, divided by mu naught and mu r1 is 6. So this is H1 milliampere per meter, as it is milli. H1t can be written as H1 and AN cross product. We can, if we will do this, then we will find the H1t. Similarly H2 cross AN12 we can find like this. This will give the tangential component and it will be J. So H1 and H2 is known from here. Put the value here to find the next unknown. So put B1x AX plus B1y, or we can say B1 AZ. The cross product of this with AN is from 1 to 2. It is normal to Z, normal to the plane, that is AZ direction, divided by 6 mu naught. This is at this place, and for this place H2 we have 5AX plus 8AZ divided by 4 mu naught. The cross product of this with AN12 is nothing, AZ plus the constant J. Now try to simplify this. Similar to that, X, Y, Z. From there the cross product of this will give the third one. So the cross product of AX and AZ, X and Z give minus Y. So B1X minus AY, AYZ, it gives AX, plus B1Y in the direction AX, it will give 0. 6 by 6 mu naught is equal to AX and AZ, AX and AZ minus AY, 5 minus AY, plus this will give us 0 divided by 4 mu naught. J is, after derivation we find J is the current density that is given here, 1 by mu naught in the direction of AY. Now simplify this. From here we can find, we can say 4 by 4, and it will give us minus AY divided by 4 mu naught plus 0. And if we will simplify, then we can say B1x will be just multiply this cross. 6 mu naught divided by 4 mu naught, that is 1.5, and B1y, this is one thing, and B1y we can say this is, because there is no x component, it is 0, and B1z is 8. Okay, so B1 is known to us now from here, so we can say B1 is finally 1.5 in the direction of AX, okay, plus B1y is 0, so we don't have anything here. B1z that we can have is 8 in the direction of AZ. This is our B1. Unit will be milliampere. Unit will be same as we have here, milli Weber per meter square. Okay, now H1 will be B1 by mu1 mu naught. So mu1 will be B1 is 1.5 AX plus 8 AZ divided by mu1 is this is medium 2, medium 1, mu1 is 6, that will be 6, and mu naught, if we will do then, okay, just simplify this, you will get the final value. So this is our H1, this is milliampere per meter, and this is B1. So the important point is to utilize these identities to find this.